Okay. Again, thank you all for continuing to join us today. We're going to take, on the order of an hour or so of opportunity here to talk at a somewhat different level, perhaps, about innovation. We spent the last day in significant detail going through a variety of very specific elements or activities that are innovative in the CAS project. And that is one way that we go about trying to bring new ideas and new opportunities into our portfolio and into the aviation enterprise overall for the nation. But as I had briefly mentioned in my remarks yesterday, all of our innovation is not restricted to CAS. We do quite a bit of that broadly across all of our aero centers, Ames, Langley, Glenn, and Armstrong, and across all of our programs and projects. And as I look at this particular showcase, as much as mentioned this is the 5th year that we've done this, and in these first 5 years we have focused almost exclusively on the Convergent Aero Solutions project. What I think we want to do is we evolve, and frankly we've done a little bit of that this time already, is to begin to showcase and highlight things that are impactful across a broader swath of the Aeronautics Research Mission Directorate portfolio. So we're going to take a little bit of time to do that today. Who we have here on the panel, you've already been introduced to Jay yesterday as he provides some opening remarks. He'll take a little bit of time to talk through from a mission director portfolio and some of his perspectives, also as a program manager, director up until somewhat recently, in terms of our broader innovation challenges and direction. And he'll be followed by the 3 project managers that are part of the Transformative Aero Concepts program that Richard and I oversee. And in fact, I'll let each of them take a moment to introduce themselves as they, before they come into with their remarks. But we've got Mike Rogers from the Transformative Tools and Technologies project. We've got Koushik Datta from the University Innovation, and of course, there's Isaac at the end on CAS, and he'll provide some wrap-up comments. So again, for the next hour, we'll spend some time talking through, and we'll have some open Q&A as we close things out, wrapping this up. So that being said, we have some charts, but primarily, folks, this is a conversation. Let me turn to Jay here on my left for some perspective at the mission level.
Well, thanks a lot, John. And again, I really appreciate the opportunity to be here. Before I get started into the panel thing, I just wanted to tag on to something that came out at the end of yesterday, and in talking about the assessment of what we heard. And you heard it from the VC panel, and I think echoed across the board about the quality of the presentations from the various teams from the CAS side. And I'd just like to echo that. I thought it was really nice to see, in 15 minutes being able to explain the problem in a way I think that everybody in the room could understand and get an appreciation for what was happening. So just wanted to comment on that really quick too. So turning to the topic, of course, of innovation, I'd like to start, so I think we could go around and come up with probably 20 different definitions of what innovation means. But to me, I like the one that says it's an idea or a creation that creates value, and something novel, new, but also something that creates either a new capability or a better way of doing things, something that somebody wants. And of course, that is not constrained just to the Transformative Aeronautics Concepts program, but really something that we strive for across the ARMD portfolio. So I wanted to start by saying a few things that I think that we've done to address that, but then also some areas where I think we need to continue to work to continue to push so that we can create that culture, that innovative culture across the entire mission directorate. And again, not just looking to one program and saying, it's it, that this is up for you to do. So one of the things I would argue that we've done, and really this goes back more than 10 years, that we really tried to create more cohesive collaboration across centers. And it's not just in the partnerships that we have down at the research level. I think that had been going on for some time, but also at the management level, whether it's how we're looking at programs or how we organize and structure our projects. And again, those that are very familiar with NASA know this. It's really almost something we take for granted right now. Almost, I would say, every one of our projects involves at least 2 centers, some of them across all 4. And it's not uncommon to see, say, the 3 leaders within a project team to all come from 3 different centers, and really creating that as a NASA enterprise and not just the contributions from individual centers that line up to individual projects. So I think that actually has a lot to do with innovation, because it's sometimes we also say it's the truly innovation occurs at the boundaries across disciplines, not with necessarily just within a discipline itself. And how do you to do that? You work better across different areas. Another thing that we've done as we've evolved over time is I think we've had different focus for each of the programs and the projects. We've been a little more creative. So on one end of the spectrum, you have seedling efforts that you find in TAC. We're looking for higher risk type of work. We're continuing to look at how we manage and how we work within our mission programs. And some of those might mean having a finite effort that tries to accomplish a certain goal in a certain amount of time and move on to something else. In other cases, it's how we can turn over a portfolio more efficiently, more effectively. And then at the other end of the spectrum, how do we actually take some of that innovation and put it in practice in form of like an X-plane and some of the things that we're doing in the Integrated Aviation Systems program. So we've created different means to manage each of these different efforts. So different risk tolerance that we may have, different means that we may try to manage within those. Another thing that I would say that we're trying to do right now to sort of create that culture or allow people to work more efficiently is take some risk or some opportunities in how we manage things. And so one example is, in the past, whenever we wanted to do something new, what do? We did a reorg. Let's change things and make the organization fit to where those goals are, because that'll be more efficient, that'll save time. Well, it usually takes a year to do that. And so in a 5-year project, if you spend a year reorganizing and lining up to that structure, have you really saved time? So what we're trying now is really trying to accentuate that working across program and project boundaries and more of a mission focus. You've seen this in what we're doing in supersonics. You see how we're working in urban air mobility, and the idea of trying to break down some of the walls or the barriers between these programs and projects so that we can work more efficiently, we can get on with what we're trying to do, is some of those examples. I'd also say that we've looked across the spectrum and said, hey, how do we accentuate some of the work on the more foundational side of things? And this is where you'll hear from T-Cubed and how important it is to develop some of those fundamental technologies. And I think it was some great examples in the talk that we just had. How something like that F-14 experiment made a big difference to aircraft that are flying today. And it was that fundamental knowledge that we generated that gave us the ability to take some of those creative leaps and bounds and things like this. And so fostering that, encouraging that, and you'll see that happening. And also good examples of changing the way that we do things. How do we learn and how we're managing it? And it's a delicate balance there between creating stability with which to work, but also trying something new and having that continuous learning type of an involvement. And I think this is what you'll see happening across TAC writ large, but even things that we've done, for example, within the University Leadership Initiative. And again, Koushik will talk more about that as well. So those are ideas I think that we've done to try to foster some of that creativity and create an environment that's more conducive to that. So let me shift gears just a little bit to the question I think that was posed yesterday at the very beginning of the session that said, okay, this is great, ARMD, you're talking about innovation. So what are you doing to stimulate that? How are you funding that? Or how do you draw on not just creative ideas that we implement, but actually trying to foster how do we how do we become more creative as an organization and a focus there? So I'll admit, there was a little bit of this, hey, build it and they will come. So one of the things is we created a program that tried to be a little more flexible within TAC. And I think there was a little bit of an element, well, if we do that and we say, hey, we want to manage a little bit differently, it will just naturally occur. And And sometimes these are these kind of things that you have to foster some of that innovation that we get that. So I'll say the part of the answer to that is maybe we're still trying to figure out, are there better ways that we can do things, and looking for ideas. And then part of that question also said, well, what about the resources? Where does that come from? I think it's probably easy to say, well, it's just a couple $100K, things like that. That's not hard to do. But trust me, across the, even at the project level, or the program, or even the mission director, we probably get hundreds of those. Just 100K kind of things is what it's needed. And one of the things that I'll say in our limitations, and I'll try to jump toward it, we are probably over-constrained ourselves. That gives us some of that flexibility, because it's really hard to cut some of the work that we're doing, because it's like, oh, this is really good. How do you make a decision? Well, maybe I need to do less research and more electric aircraft, less on autonomy, so that I can do some of these things. That's a hard call to make. And so we've been trying to run with this delicate balance. And I think that's a hard mix. But one of the things where the better way to solve that is get feedback, get the communication on, hey, here might be some ideas, here's some things that we could do it better. The other thing I would also say on that topic is it's not really just up to ARMD or to the programs or to the projects, but this is also where the centers come in. And when I view NASA and say, what do we deliver? What's the best value in NASA? It's not the money that we bring to it. It's not even our facilities, but it's our people. And so developing these kind of creative ideas, helping people work together, is developing our people side of things. And again, where the centers have a responsibility to do that. I don't want to just toss the over the fence and say, well, that's your problem, looking at somebody like Dan and say, you go off and fix it and come back to us and let us know. That's an area where we have to work together with the centers. And I think that's another area that we've built up over the years too, is that working relationship. And we've had a lot more discussions writ large on the topic of capabilities, and I would put this kind of under that of how do we better develop people so that we can accomplish the mission. And so I think the best way to do that is working together. So that was my answer to the question that we had yesterday about how to move forward. And part of that answer is I don't have all of the answers, and we have to work that together. And that brings me around to some of the things I think we can also work on as an organization. I mentioned one of those. We definitely over-constrain ourselves, and sometimes it's that having a little bit of flexibility, holding money back in reserve and allowing us to take some advantage of some of these opportunities, and having the discipline to do that is something we need to continue to work on, and we're all trying to do that. Another thing I would say, though, too, is, and it's a common thing for when I get a chance to talk about, it's taking technical risk. When I was a program director, I would say after our program reviews, I think the comment I had every year was, it still feels like we're too green. Like we're accomplishing almost everything we set out to do, and if we were really trying to push the state of the art, I think we would see more elements where we don't always do that.
Too green, meaning on a red, yellow, green level of success. That's right. Okay.
Yeah. Oh, not too green and not too
environmentally.
Please don't misinterpret that. But it's that idea that it's okay to take a chance on something technical. We talk about things like, hey, we want to fail fast and learn and then move on. But do we really do it? And I'll pull one example, and that's from yesterday in Kurt's presentation when we talked about, hey, we tried a really hard problem. We came to a decision and said, you know what? It's just not ready. It's going to take longer. It's time to move on to something else. That is a very hard decision to make, but I think that is something that needs to be applauded within the organization, and we don't do enough of that across the board. And I'm guilty of that as much as anybody else. I mean, we talk about go fever on the space side. We get it on the research side of it's just going to take a few more months. We can just put a few more dollars into this. When the right answer may be, let's take a step back, regroup, and maybe work another problem. Because one thing we don't lack is problems, ideas, and things to try. It's the resources that we have to go after those. And it's that kind of combination. And then the final thing that I'll say that I think that we can also work on is, as a group, we've gotten better at working in diverse teams and pulling things together, and I think that goes back to some of the things that I said. But sometimes we're still afraid, I think, sometimes to talk about the challenges that we have. When we've got a new idea, we tend to want to talk about what's working well, and I think it leads back into the thing I just talked about. It's part of that success-oriented nature. That is part of the NASA culture. But in order to be innovative, we have to stand up and acknowledge, hey, these are areas that we have challenged. Open those up for debate or discussion. So maybe one thing I'll pose back to the CAS team is it's great to talk about like what we did yesterday, but maybe a little more flavor, especially for some of the areas or the projects that are in the earlier phases. hey, these are the problems we're running into, and we'd like ideas on what other people may bring to solve those, and work those collectively. Because it may be somebody that's working in a completely different branch, different area that says, you know what, I understand the problem that you have now, but you know what, have you thought of trying this? Have you thought of trying something else different? And that's where I think you can truly spark some really innovative solutions. We don't do that because it's a lot easier to talk about what's going well than the things that we're stumbling on, because I mean, there's a pride element of, if I just work hard enough, I can solve it. But the real way, I think, to get it done is to draw on the NASA team. And by that, I mean not just the civil servants, but our partners and everybody else that we have to work these problems together. And so I think a little more focus on where we're doing there, I think, could help us move even faster. And trust me, I've had a number of people say, hey, you know, we don't want to bring things up to that's bad news up to headquarters. And sometimes it's okay to do that. So I'll leave it at that.
No, that's a great comment to close with, because in part, that's something that we, as leaders at headquarters, need to be aware of. Sometimes they come with problems and we can be too helpful, right, from DC. And that's not always valued or appreciated in quite the same way as just listening and trying to make the connections with their external partners to help bridge that in a more collaborative innovation than the kind of help that we often bring.
Or the feedback, to add to that. In some cases, because you know, we're guilty too. We talk about wanting to move fast, and then we take 6 months to make a decision. Well, that's not helping anybody. So the feedback on, hey, this is what really helps us, this is what moves forward, and having those open lines of communication, I think, are essential.
Great. Jay, thank you.
Okay.
Let's move to a project level discussion. Mike, I mean, in fact, anyone who want to take to the podium, that's fine, or have a seat, whatever you're comfortable doing.
So the charts.
And yeah, Mike, Ricky, get them up. Beautiful. Thank you.
Good morning.
They're coming.
As John mentioned, I'm Mike Rogers, the project manager for Transformational Tools and Technologies project. It's one of the sister projects to CAS. Like CAS, we're a seedling project doing sort of foundational work in the spectrum of things, higher risk, potentially greater payoff work that may take a little longer to complete successfully. We are sort of the last bastion of deep dive discipline research in NASA aeronautics, really. So some of these areas, they're sort of maybe less applied, more just trying to really go after deepening our insight, understanding the physics of the problems so that we can better model them, better build systems of the future. So I'm not going to do death by PowerPoint here. I just have 4 charts just to talk about some of the things that T-Cubed has been involved with. I put this one up first because currently this eco-demonstrator Boeing flight test vehicle is flying right now with our hardware on it. So what is this hardware? These are vortex generators. They're very particular vortex generators, and I'll get to that in a minute. So aircraft need these vortex generators, which are just these small vanes to control the flow so you get the right kind of control and behavior on takeoff and landing. As you get up to cruise, where the vehicles have a lower angle of attack and are flying faster, you don't need those. And the way they are on planes right now today, they're just sticking out there in the flow and creating additional drag. So what if we could think about something that would stow that vortex generator at cruise? We could save some drag and reduce fuel burn. The challenge is if you had to run electrical wires in a control system all the way out to those things along the wing and then carry that extra weight on the plane, you'd probably lose some of the benefit you got in drag. So what ideally we'd like is something that you could just put out there on the wing and it would know when to put itself down or to put itself up. So you have to ask, well, what kind of a stimulus do we have that's different on takeoff and landing and at cruise? And one of the big obvious ones is temperature. As you fly up to the cruise altitude of 36,000 feet or something, the temperature drops significantly. It's much colder up there. So could we envision some kind of a system that would stow itself, change its shape when it got cold? And the answer is yes. T-Cubed has been doing a lot of research in what we call shape memory alloys. And you can see some of our tube-shaped shape memory alloys there. These are steel rods that the material inside changes phase with change in temperature, and that creates a motion. And you can train these things so that they twist when they get cold and untwist when they warm up again. So we'll put these rods along the axis of that vane, and at takeoff and landing, we've trained them such that they're up, and then when it cools off, it moves and stows away like that. So that's incredible. And these things are flying out there, and they're doing that. So that is a kind of a technology, and this is what Boeing Eco Demonstrator is for, is to try and test technologies that are close to being ready to put on the next vehicles Boeing is building. And I'm optimistic that we'll be seeing these things on planes in the reasonably near term. Now, the challenge is here. How did we happen to know what material to use so that it was at ambient temperature in, say, San Francisco up, and at negative 70 degrees Fahrenheit down? You know, how do you know how to pick your material properties, your material to do that at the right temperature locations? And it's a lot of trial and error. So that can limit us. Now, our folks at Glenn have been doing it for a long time, and they're building up an understanding of what you have to use here. And these are nickel titanium with a little bit of hafnium. But you could add a little bit of zirconium or mix in a fourth thing. And of course, that's going to take a really long time to try and go through that entire space of things and map out exactly what those transition temperatures are for all these materials. So we've taken another step in T-cubed, and this is a big part of our project. Can we do it computationally? Can we take the equations governing these kind of physical properties and with a supercomputer, like the one we have here at Ames, understand what that transition temperature will be for different compositions? And you heard from John Lawson yesterday in his work about batteries. Well, his team has also worked with shape memory alloys, and what I'm showing over here is a map that is constructed from computations. And these are very intensive computations that get down to kind of the molecular level and understanding what that new third and fourth element we add does. And you can see built a phase diagram of the composition of the third component you mix in with the nickel titanium and the temperature at which the transition between those states happens. So that's incredible. Because Boeing right now, one of their questions on this flight is, well, what if we take that up to Alaska? Will it still work, or is it too cold? Will these things not be up on takeoff and landing? If we can dial in the transition temperatures we need computationally, we don't have to spend a lot of time trying to find the right material. We can design the material from computational means from the governing physical equations. Okay, so here's a second example. This is again focused on computational tools, and this is so-called computational fluid dynamics, trying to understand the fluid flow over an airplane. And we right now have what we call a technical challenge, a 5 to 7 year kind of effort focused on trying to make a significant breakthrough. In this case, it's predicting the maximum lift coefficient on a commercial transport. What does that mean? Well, as you know, when you get in a plane on takeoff and landing, pieces of the wing come forward and back to increase the area. There are gaps in there. Those gaps are supported by brackets that hold those pieces on. That's quite a bit of additional geometric complexity, and as you see from this Boeing chart I borrowed, we're collaborating with them on this. There's a lot of flow features, vortices coming off of the different pieces that are very complicated. You know, our current aircraft industry uses a lot of CFD to do their design, but they're using things called Reynolds average Navier-Stokes approaches. These are approaches that just try and predict the mean flow profiles of the various quantities of interest. And when you do that over the whole vehicle, you can get things like lift and drag, and you can do pretty well at designing for the cruise point. But when you start getting these more complicated configurations and you have things that are separated flows where the flow longer stays attached to the eddy or these big vortices that have been created, then it gets a lot more difficult. And in fact, these RANS methods, these RANS CFD tools can no longer accurately predict that kind of a complex flow. So we've been looking at more complicated CFD approaches that try and not just get a mean average flow, but predict some of these turbulent eddies that are in that problem, a more general capability that actually solves for the large eddy structure, the large turbulent motions in there. Those are, of course, more expensive computations because you have to use a lot of grid points to capture those kind of complex turbulent motions. But if we could do that effectively and efficiently and predict these kind of flows, what would be the potential benefit? Right now, for Boeing to build a completely new plane, not a derivative one, they have to undergo up to 2 years of flight tests costing them about $1 billion a year. If we could increase confidence in CFD tools that we can design for these kind of things, they would have to do fewer flight tests to verify to the FAA that, yes, this vehicle is safe and is working as designed. And this high lift configuration, this part of the flight envelope, accounts for about 2/3 of the flight test points they need to do, mainly because CFD can't do it very well yet. So if we could cut the number of flight test points in half, we save hundreds of millions of dollars and a significant amount of flight time in getting their next product to market quicker and more effectively, avoiding surprises that we get in flight test. So right now, we're embarking on this effort. You can see a wind tunnel test, a JAXA wind tunnel test, a partnership with the Japanese NASA, effectively. This is an oil flow visualization, and now our new eddy resolving kind of approaches, doing much better at predicting the flow over that kind of a wing than the RANS computations can do. All right, one thing we need if we're going to be doing these more complicated CFD calculations where we're trying to get the turbulence, not just the mean and lift and drag, then when we go into the tunnel, we better measure more than just in lift and drag. We better measure the turbulent eddies and the details of flow separations. And we need to actually commission special so-called validation experiments, which contain some of this complex physics and make a strong effort to measure everything we need to really compare apples to apples and experiment to a computation on the computer. So there's no ambiguity of, is the modeling good enough or not? You know, what is at fault for any discrepancies? So we need to be able to get good measures of the turbulence, and you can see here what's really innovative about this is we're actually trying to get near wall measurements of turbulent fluctuations in the so-called separation bubble where the wing attaches to the fuselage. What happens there, because of adverse pressure gradients, the air that flows over the wing can no longer stay connected to the wing. It breaks away and lifts off. That creates a lot of drag. We need to be able to predict that to avoid problems. The challenge historically by using laser measurement techniques coming in from the outside is you get reflections off of that corner area and you can't get measurements of the turbulent behavior there. We've overcome that by putting the laser instrumentation inside the fuselage and looking out there. And another benefit, if this thing is vibrating a little bit, the measurement stuff is moving with that oscillation. So this is pretty neat. We had this juncture flow experiment in the 14x22 wind tunnel at NASA Langley. Got a great data set that's going to be used by the entire community for improving models to predict this kind of separation. In addition here, you can see we need to measure more than just stuff on the model. We need to go measure everything about the inlet flow of the tunnel so we can match that in our computation. What's coming into the computation has to look like what's coming into the tunnel. You can see the Boeing QWiz instrument measuring everything about that inlet flow. We need to measure the wall behavior. This tunnel is not really in ice, ideally when Boeing flies their planes in a flight test, there are no tunnel walls containing the flow. So we need to understand what is the effect of those tunnel walls. We need to measure all the stuff on the sidewalls as well as the stuff on the plane and the stuff upstream so that when we put a computational grid around this problem, we know exactly what the boundary conditions need to be to get a match. And finally, we've heard a lot of talk here about electrified aircraft propulsion. That's a relatively new area for NASA, and there are a lot of new challenges in terms of enabling this, and it's not just the traditional aerodynamics we were talking about previously, but a lot of things that haven't, involving electrical work, inverters, motors, things that we may not have been heavily involved with. And there are a lot of challenges in doing this right. If we're going to be able to get an efficient system that can compete with what we have today, we may need higher voltages routing through these cables than what are in aircraft today. The materials for that don't really exist yet. There are problems, particularly at altitude, with arcing and stuff. We don't have the insulators. We don't have the conductors. We don't have those materials yet. And this I put up as an example of where a few years back there was a CAS project trying to look into what it would take to get high voltage, high frequency power cabling as part of one of the electric aircraft efforts. And this is a case where our more enduring research project saw a lot of value in this, particularly for NASA's futures priorities, picked up this effort out of the CAS effort and is continuing to develop that work on a longer research timeline to be able to deliver on some of these components that were going to be needed for electric aircraft. Another example, energy storage. You heard John Lawson's talk about their work in batteries. They made a lot of progress in terms of understanding the physics, looking at different electrolytes, but they didn't really create a battery that's going to function for that next generation of electric vehicle. We're looking at picking up some spin-offs from that work and building off, just like we have with the shape memory alloys, the ability to really design for these components, to design the material so we can come up, rather than experimenting with a million different possibilities, really narrow down the design space to what will work for our application. You can see the shape memory alloys there. Some of these actuators, particularly in small spaces, could be used when pneumatic stuff is too heavy or won't fit. The Cambium motors, a lot of all this stuff. And T-Cubed is looking to develop some of the foundational materials capability, foundational computational capability, to bring this forward so we can enable some of these concepts that the mission programs are looking at. So let me pause there and let Koushik talk. You want to advance one more?
It may be a separate file. And Michael, thank you very much. Great. Yeah.
Very cool, Mike. I like those. So I'm going to talk about University Leadership Initiative. I'm Koushik. I will also be referring it to as ULI, so remember that acronym. So NASA has been working with universities for many, many years, and we have been working with them in different functions. ULI is slightly different, and previously we have been working with the universities. We'll tell them the topics that we are interested in and ask them to propose to it. Here, ULI has been running for a couple of years where NASA Aeronautics decided, let's try an experiment which is slightly different, where we will ask the universities to propose, what barriers that they want to overcome, what is that aviation challenge that they want to hit, and so we ask them, go ahead, propose those challenges, tell us what is the way that you will come up with new concepts that will overcome those barriers, and put up your own teams the way you feel. But we want you to be also looking at training the next generation of engineers. So start including undergraduate engineers into the engineering students, into the research, introduce them to it so that they get used to real research associated with NASA. And as you'll hear, as I've heard from many of these universities, the students love it and come in droves to want to participate in a research of that type. So we have asked them to do that. In addition, the other thing that we have realized is that most of our NASA funding does go to universities that are very recognizable to all. We wanted to spread the diversity around, make it represent more of what the US is all about. So we have asked them to mentor some of the minority serving institutions, bring them in with the team so that they can eventually get into the NASA Aeronautics ecosystem. So, and that has also been working well. As you can see, we have just done 2 rounds of awards, 5 awards in the first round and 3 in the second. And we have asked, because they're looking at system level problems, they're looking at multidisciplinary solutions, so they're bringing in, so these 8 university teams actually end up become 34 universities plus their, you see number of companies too associated with it. So you can see that it spreads out quite far, quite wide and across so many different states. We're also having over 150 students included in this, and about a third of them are undergraduate students, including in some cases, some of these universities are going to high school students and getting them involved. So we are seeing a lot of different types of things that maybe we didn't expect, and so this experiment is working out well. The other part of the experiment was that we would, since we asked them to provide their own work that they want to work on, we just evaluated. We also said, go ahead, bring your own peer review team in and do the peer reviews by yourself. NASA will just sort of look at your annual meetings and your quarterly meetings and get some insight into it, but the reviewers should be people that you have brought in. So we never knew how it'll work out. It's turning out, and initially we thought about it and we were thinking that it'll be mostly the academics and they will fight against each other and they'll do this. It's turning out completely differently. The industry folks, almost all of, about more than half the people that they have used in their peer reviews are industry folks, because we tell them that we want you to transition your technologies too. So they're bringing in the right type of people from industry, and these people, they may not say it openly, but they're certainly working in the background and telling the faculty to change their research or move their research in certain directions so that it'll be useful to them. So we're seeing a lot of that, and as an example, I just went to the Ohio State annual meeting last September and talked to one of the peer reviewers, and he's from Aurora. His name is Ed Lovelace, and he's working with Aurora. And I told him, most of it is about the drive, the motors, and the electronics. What do you get out of this? And he just told me that everything that Ohio State is doing in terms of the battery management, the testing and the battery management, all those techniques Aurora has already faced, and they plan to use every one of those things that Ohio State is developing. So it's really cool how people are seeing the value in it, and the industry is coming on to do this. So it's working out really well. And then, for example, one of the other awards that we have given is developing new communication systems for the NAS, for the National Airspace System, and this was led by South Carolina. The University of South Carolina team came up with the new filter band multi-carrier method for the data link for the L-band services, and their reviewer was Boeing's Greg Saccone, and Greg realized the benefit of it, and he's going to put that up in a fairly, maybe next year, and I can't call it, but it'll be a flight demonstration, and if it goes well, this will be part of the data link, and if it goes well, they're already calling it that it'll be an L-band data, LDAX 3 type of a standard. But standards also take a long time to go through, but this is how things are happening, and it's really mostly through the industry rather than the academic peer reviewers. We have had different types of awards that we have given. Some of them are to the near term, near and midterm, just like I talked about the communication systems. Some of them are helping, new ideas, like things that we are working on, which are sort of changing the landscape, which is in supersonics. So Texas A&M proposed a topic where they will sense the atmospheric conditions, say 25 miles ahead of them, and these atmospheric conditions are important for the sonic boom or the noise that the aircraft makes. So once they sense it, they're going to take back the information and make small changes on the outermost line so that the boom or the noise that'll be over when the aircraft flies over 25 miles later will be reduced. Of course, they pay for it through drag. So that's a cool, cool new technology that they're developing. Then there are some other things that we are sponsoring, for example, is completely new concepts. And this is a University of Illinois-led effort where they're looking at superconducting materials and hydrogen fuel cells so that they can develop a whole hydrogen-fueled aircraft. So we are seeing a broad range of ideas come in. We get a lot of good ideas. It's really hard to choose. John has the unfortunate, or the fortunate.
Good fortune.
Good fortune of narrowing down and only awarding the ones that we want to award. I mean, still, it's working out really well. And of course, I talked about one of the goals being the engineering students. We are already seeing that. Honeywell has grabbed some of the South Carolina students. Boeing has told me they're going to take some of the University of Tennessee students. And, it's just, and then even at an, AIAA meeting, there was a MITRE person sitting next to me listening to some of the Arizona State University students and says, those are the people I want in my team. And so he wanted the contacts. So it's working out pretty well from all the goals that we have set for ourselves in terms of, increasing the diversity of researchers that are working on aeronautics problems, the students, the future workforce, and we are affecting the aviation outcomes. So I think I'd like to stop with that.
Yeah, Koushik, thank you. So, again, the three projects that we have in TACP are T-Cubed, UI, and CAS. Although Isaac was able to provide us many earfuls of information over the last few days, wanted to make sure that he had a chance to talk about how how we fit CAS and those objectives into this larger program landscape.
Yes, thank you, John. As you probably will know by now, I'm Isaac Lopez. I am the program manager for CAS, and I have the benefit of having the previous day I have all the PIs present all our work. So starting with some ahead in that area. So I'm going to talk for a few minutes. But let me tell you, CAS is, we have two main goals. CAS is about a proof of concept, if you will. We try to develop concepts and we try to make them to see if they are feasible. So You heard them talking about the feasibility of their study. So we basically say, we have an idea, we want to prove that that idea is feasible. So we give it a short time for execute, which is like around 2 years now. Used to be up to 30 months. Some of them are still working at 30 months frame, but the new ones have been given only 24 months to prove their proof of concept. If they were feasible or the work that was done was successful, and sometimes successful, they could prove that it was not feasible, but still the research be successful. So completing the feasibility is the successful the study. So the work could be transitioning on to some mission projects for further development. So we would, again, the idea is just to prove that the concept is feasible. Somebody else will actually develop the concept. The other thing that we wanted to do in CAS is to develop the workforce, introduce the ways of working rapidly, different pace of what NASA is used to, and also bring a new early careers to the mix. We have experienced that early careers really enjoy working for NASA and what type of work that we do. So that has been very rewarding to do. So so basically, you saw we are multidisciplined, a little different from T-Cube. T-Cube sometimes is deep down, like Mike mentioned, but we do multidiscipline, more a system level. So some of the work that Mike has been developing for some years, like SMAs, we came up with an application to do put it in a wing and be able to twist the wing to improve the performance in the airplanes. And we do some study. The work that we learned went back to some of that to T-Cube to continue the development of the SMA. So we have had some interactions with T-Cube in some partial, and Mike mentioned some of those that we have had throughout the years. One of the things that we hoped, as Jay mentioned, that build it and things will come. So we have built some, but like he also mentioned, sometimes when activities has to go to some of the mission projects, you have to drop something to get something, and that's not as easy. It's a lot easier said than done. So we having not as much success as we had hoped, but we're working on that as a mission director. We're also looking to transition that to the outside, and we have had some limited success on that. But we continue to build on the lessons learned that we have had, and we hope to continue improving in that regard. Some of the things that also following on Jay said, that we have to bring things that not everything is great. Sometimes things are not as good at. We talked about rapid pace, doing things in 2 years and moving very quickly. We talked about doing that, but we have found that we ourselves were not ready to move into that fast pace. And not only project on some of the activities. We like to do it quick. It's like we have a momentum of energy, and we cannot break that. So we're dealing with that, and hopefully we'll get over that. But getting into these fast pace of development is something that we have had some issues grasping to, and we need to get over that. So anyway, so just an example. We're working on things. We need to get better, and we have a bunch of lessons learned that we are trying to apply to ourselves. We are built upon the theme of build, measure, and learn, and we keep learning, never stops. So with that, I'll stop.
Great. Isaac, thank you. Koushik, Mike, Jay, really appreciate the comments, reflections up front. We've got about 15 minutes, maybe 20, and I would very much like to give you folks the opportunity to ask some questions. I want to start, however, with this second question that we have here from the conference I/O. I mean, you heard Isaac just talking about the length of the CAS activities that we heard yesterday, on the order of 2-year efforts. Koushik talking about his ULI awards, 3 years, 4 years, 5 years. He has a range of those across his project right now. Mike talked about the technical challenges as 5-year chunks of work. And as Michael is developing his discipline-based expertise in order to do that, both Isaac and Koushik are trying to infuse new people and technologies and approaches. Can I ask our project leads, how do you see that working in terms of the way that you are each interfacing with these, with innovation and these shorter time frames? Are we getting enough out of it? Do we have the feedback between the three projects in order to do the best innovation at the best level? What are your thoughts on that? And any one of you.
So yeah, there's a challenge there, and I think TQ being the foundational discipline research, a lot of our stuff is a very long timeline, and even for us to fit in that 5 to 7 year tech challenge range may seem too near term for some of it. We have, as part of our work, commissioned some what we call vision studies, one for CFD, which is titled Vision 2030, and that's sort of more the timeline that we suspect could really have an impact where our tools could do most of what we need them to do on that kind of a timeline, and a comparable study 4 years later for Vision 2040, which is computational materials and structures, which is relatively more in its infancy, I think. I think there's a lot of things where applying our latest supercomputing capabilities are going to really enable some progress in what we can do in that vein. But those are necessarily longer timeline goals. So I think these tech challenges, they're pieces of that bigger vision, of that really complete overhaul of our ability to analytically predict some of these physical processes and physical behaviors of materials. On the other hand, if we say, well, we don't have any interesting results for you now, we'll talk to me again in 2030, our funding will dry up really quick. So there is a balance of how do we find useful chunks along that path that are going to have an impact. For instance, with Boeing, this ability to predict CL max, even though it's just one aspect of everything we'd like to do for Vision 2030, would have a very significant impact on their bottom line, on their ability to bring new products to market quicker, to outcompete competition. So when we think we're at the point where we have a good promise that these new tools we're working can actually have that kind of an impact, then I think the 5 to 7 year timeline is realistic. We don't do too much in T-Cubed on the 2 year kind of timeline. That's more what CAS is doing, but we do maintain a very close relationship with CAS to try and identify those things that are showing promise, or those things that are doing things completely differently that could really revolutionize the way we look at stuff, and pick up those pieces and try and grow that where appropriate.
I will just comment that one of the things that we have done very good at CAS is to form some of those teams. It will be, I was amazed at some of the teaming that we have made. One of the things about CAS, we have to be multidisciplinary, and that means bring the right disciplines to solve that problem, and that usually brings different members from different centers, and also brings industries, non-traditional partners, if you will, that we like to bring in to work with us. So we can have, our title is Convergent. We like to bring different lines of thoughts to try to solve the given problem that we're trying to prove their feasibility. So we have created some great teams. We have examples. Sol was a great example. Shell, Pat is around here someplace. We have an outstanding teams, and sometimes they come back to me at the end of the time and say, Isaac, we have this great team. How can we preserve, the teaming and the work that we are really working very well together? And so I think that we have been very successful at building the teams. Now, on the part that would be enough to maintain the effort, well, because we finished the feasibility, and the issue becomes, if there's not something to continue the work, then the team gets dissolved at that time. But I have been amazed to how good we have had some of the teams that we have been able to put together, and all the kudos to the teams themselves that they have done that. So yes, we have had teams. The issue is, sometimes after the 2 years, what we do with that great team that is really working together, and a little bit more say that doing this way, the PIs have said, hey, I now have friends in my other centers that I have never thought that I that I will have. So working on CAS and giving them that experience. And that, even though that they might move and the team will be broken, they still have those contacts and they will be used in the future. So that's something that will continue to give results down the road.
So John, I know that this question was probably meant for Mike and Isaac specifically, but I can talk about the university aspect too. The universities are allowed to propose for many different lengths of time. Many of them are proposing at the 3-year level. They think they can accomplish something, but that doesn't mean they're going to end doing that work. They really are parlaying that for future other work. They see the NASA brand, they're getting the award from the NASA brand, helping them get future awards. We've already seen that in a couple of our universities. They have started setting up complex, centers that go into further, like in Arizona State, they set it up with the other 2 Arizona universities, and they're going to continue studying this, and they're getting funding from other sources, including NSF. And in the same, the communications thing that we talked about, South Carolina, one of their partners, NC State, essentially proposed advancing it for 5G and drones and doing that for communications, and they got a $24 million award from NSF and industry. And I could go on, but Ohio State, they're getting grants, and so no one is really thinking about standing still. They're really planning for the long run. And of course, there's a second set of things that you worry about, which is the graduate students. The graduate students still have to do their let's say the master students is not an issue. The graduate students still have to do a PhD, but they get sufficient amount of work from any of these awards that they're doing, and really good, realistic work that they can finish their PhDs with the efforts that they started during the award time.
Jay, did you want?
Yeah, no, I'll just a couple of comments on that 2 to 5, and again, this is just my personal belief and perspective on that. One is, if you look at the pace of innovation in the world around us, I mean, kind of going back a little bit to what Mike alluded to, the world is moving fast, and so if we say, well, it's going to take 10 or 20 years to see anything, or have that, and I know that's not what people are asking, but the quicker we turn around, the more likely we're going to see an impact, to the world and get back to that part of the innovation equation of making a difference or having value. So there is a time element that is important to people, and so being able to do that quickly. But I would argue a more important reason is I think that it makes us as a team better problem solvers. If you have an opportunity to move to different teams within 2 to 3 or 5 years, periods, and so over a course of 10 years, you may see 3 or 4 different ways of working on things, different ways of attacking problems and approaching that. I think that makes an individual a better problem solver, because they've seen a variety of ways. And so picking up on these great teams that we've built, okay, we've done that. How can we then share that experience and build other stronger teams, or augment a team that may be working and bring some of those new ideas to that? So it's working in that kind of way that I think the more we embrace it can actually make us more creative, more innovative, rather than thinking I've got to stay, on one effort for 8 to 10 years in order to make a difference in solving that. Now, that being said, some of these challenges are going to take 8, 10, 15, 20 years, but that means we can break it up into the component parts of those problems. I mean, it's a natural engineering breakdown on how we solve those problems. Make a decision. Is it worth to continue in the direction, or is now a good time to pause, reset, maybe take a different change? And that's why breaking it up into these chunks, I think, also makes that a little bit easier to do. So just my comments on it.
Great. I'm seeing that we have a question that has climbed the leaderboard here very rapidly. I want to get to that, but before, is there a question from the audience that someone would like to ask before I go to I see Anna McGowan over here. It is Anna, yes? Did I get you? There you go. Good.
The question is that CAS values cross-center collaboration as well as cross-discipline interaction. I think everybody in this room, thanks, likely values that as well. However, similar to the first question, the ability to work across centers, or to know who to contact at another center or who to work with in our branch that's not in your building or directorate, it rests solely on the PI having an epiphany or having a lunch meeting or something like that, or just who they happen to know. So this unfortunately penalizes introverts And it also penalizes those who are new to the agency, whether just because they're new coming here or they're just younger employees. So how do we get to either how centers operate or program offices to support the kind of cross-disciplinary, convergent type of things that we all know is helpful, rather than just saying, go do it, good luck? What are your thoughts?
Okay. So I'll make a very quick comment, but then turn to the folks here at the table to help. I will agree that there is a large burden that's been placed on the PI. To suggest that it is given to them exclusively with, go do it and good luck, I think misrepresents the system that we have in place. The liaisons at each of the centers and the center ARDs in that office are taking a very substantial role in supporting those connections and the engagement. Is it working as well as we would like? No. So from that perspective, your comment, and maybe, Anna, that was your initial question that came forward, I think is still a very fair one, because we need to do a much better job. The importance of multidisciplinary work and convergent work across industries and cross centers is a highly valued and critical part of these proposals and this work. And if the PIs cannot be given the help in order to do that well, we're not going to reach our objectives and our potential for this. So we need to do that better. But let me stop there and again turn to Jay and others down the line here for any comments they may have.
Yeah, so one I would say is, as granted, kind of what John said, there's a lot of responsibility to the PI, but it's not exclusive to the PI. I mean, they're forming teams, and it's got to start even within the own center. And drawing on that experience of others around you that, hey, what have you done? If you're sitting at Langley, what have you done to work with Armstrong? Finding the people that have and branching out. And it gets a little bit to what I was alluding to earlier, talk about some of the challenges. Hey, I'm having trouble reaching these boundaries. Start asking for help. And this, goes back to where there is some construct within CAS. I know they've even made efforts to improve on some of the virtual capabilities, the rooms that we have for enhancing some of this collaboration, so it's not all travel. So there's steps that have been taken, but if there's ideas that could enhance that and make that better, I think, feeding that up. I would also say events like this are a great example of it. People are represented across all centers, a chance to start working some of these. And so taking advantage of what we're doing is important. Finding creative ways in what else we could do and floating those ideas up. And I would say probably a nexus for that is also at the ARD level in building those connections across centers. But if there's things that we can do from a project program or mission director perspective that would help, we're open for ideas.
Great.
Yeah.
Isaac, I saw you raising
Yes,
hand.
I will add to that yes, we have had a process to identify partners across centers. Usually we have, like John mentioned, 4 center liaisons that the researchers at each of the centers work with. So, and then the 4 PIs talk to each other. So if they need some discipline that resides in another center, the 2 center liaisons talk about the 2 centers, and then they put in contact the people that need to talk to, that they need to talk to. So I will say that we have had success in that regard. Are we fully successful? Obviously, now we have to improve. And like I said earlier, we have build, measure, and learn. So we have some lessons learned. We continue to improve. We were doing a process which we have changed and moving into a different one, but the lessons learned will be applied for the future. But yeah, we have those 4 contacts at the centers that their job is to know the research that is happening at each of their centers. So if somebody else needs some of that discipline, they will be the helpful contact to make those researchers' contact possible. So so we will continue to improve on that, but we have mechanism to help on that.
Okay, we have just another couple of minutes. Is there another question from the floor?
So you want
You're going to get to that before.
Yeah, the top one.
Okay.
You want to do 6?
Okay.
So you
Go ahead,
so you want me to say something?
please.
So it says the burden of transition is placed only on the PI. That might not be completely an accurate statement from my point of view. Yes, the PI is principal. He knows the technology. He's passionate about their work. So yes, he's a principal on that. But we even added a transition manager. Jessica is over there, that is supposed to facilitate the process, make the contact, get the things done. So so we are helping through the process and basically being a broker to in the process, so we can put the people together so they can talk and do and continue. We also even are working on metrics about how well we go through the process of contacting SME, contacting sub-project manager, project managers, trying to get to the stage in which they agree to fund. So we are working, but at the end of the day, yes, it's the burden is not in the PI. Obviously, we're bringing something forward. In the other end, they have to be somebody that will receive it, and there is some truth to that in the things that are planned for 5 years. So it's very difficult to get something very quick. But part of what we're trying to do is change the NASA culture in which we can bring things quicker than what we are used to. So that's something they're learning, that the whole aeronautics mission director has to do. So so I won't say that it's as bad as the question looks, but we still have to do some improvement on that.
Yeah, so from a perspective of T-Cubed, we've benefited greatly from the CAS transition manager, making sure we're fully aware of all the CAS efforts in the pipeline, which ones are coming close to completing, and therefore looking for opportunities to transition. And that has definitely facilitated our awareness of that and our ability to plan in advance for having enough resources to be able to pick up pieces of those efforts. Now, I think one of the challenges is, there are 3 to 5 CAS projects a year. We can't in one project pick up that much new work. So there's going to be some filtering that has to happen. I think originally when CAS was created, they thought, well, not many of them will turn out feasible, so we won't have this problem. But most of them are turning out feasible and are looking for a home for further work. So there's a little bit of a mismatch there, and what we see happening is we may not be able to take every year something lock, stock, and barrel, but sometimes pieces come on and we bring those in with other work we already have going in-house, particularly in some of the materials work for like EAP, and we're building our portfolio by sort of picking up pieces of CAS as those efforts complete. So our efforts, the tech challenges are 5 to 7 years, but we're not entirely tech challenges. About half of the portfolio is just in enduring discipline research work, which has a little more flexibility to it. And our tech challenges aren't all synchronous, so some are rolling off and new ones are starting, so there's opportunity for funding to be available to do new work. Not as much as we'd like maybe, but the flow, there is more of a constant turnover, and we do have the ability to pick up pieces, although typically not entire CAS efforts.
Yeah, I'll comment on this one. So I talking about our problems or the things that we struggle with. I'll admit, from a mission directorate standpoint, this is probably one of them in striking that balance. I'll say it's multifaceted. At the beginning of CAS, to be fair, because I sat on a number of the casting efforts, there wasn't a lot of discussion on, well, what's the transition path? So what was the expectation? In the PI's mind, it may have been, well, this will be a natural fit for, I'll pick a project, AATT. But nobody discussed that. So is AATT looking at that? Is it, from the vantage point of sitting in the room, we might, that's something the industry will pick up or somebody else will want. And then at the end of the day, you're kind of left, the PIs, well, I thought this is where it would go, but we never really talked about it. It really comes down to setting expectations. And I think that was one of the things maybe that we struggled with from the very get-go. And you kind of alluded to it, Mike, as well, that said, hey, we didn't think as many of these would transition. And in fact, when we briefed our David Newman, who was real excited about innovation at NASA, our previous deputy administrator, I think her comment, and I don't remember exactly what she said, but it was something like, if more than 30% of these go forward, you're probably doing something wrong. So another way to look at that problem is, have we set an expectation that everything in CAS just needs to transition? Are we setting the bar high enough for what we should be trying to accomplish in a CAS type of effort? There's 2 ways you could look at that question. And that really is a responsibility of all of us, and especially up at the top when we're setting expectations. And I think that learning that we've had over these last few years is driving some of the re-looking at CAS and reinvigorating it. But some of those expectations are also what we placed on the other mission programs, because it's, on one hand, we're saying, hey, this is CAS, this is great, let's transition. On the other hand, we're turning to our mission program saying, focus on critical commitments, not 1,000 flowers blooming. I want to see more focus, focus, focus. Those two are not compatible type of directions, and that's on us, in communicating and setting some of those expectations. So I'd say it's an area that we've all learned from, that we need to continue to improve. But I mean, holding the mirror up, it's as much at the mission directorate, program, project, but even to the individual efforts. And I think the way Mike talked about it is, how do we actually view transition and success in this area? And to me, it's a little more about learning, and sometimes that learning is in what not to do or what problems I need to attack next, that we also need to view as success. And so it comes back around to that, what are our expectations for success out of CAS, and measuring that, because it kind of gets down to the other question that came up, and maybe we won't have time to get to it, is, it's hard to do, and how do we do something at a review? That's an area we have to collectively work on, in order to have that kind of culture where being able to propose something, try something, learn from it, but not be as successful as you want, and move on and solve another problem and take that with you is part of that culture we need to continue to enhance.
Great. Okay. Folks, thank you in the audience for your engagement and questions, for the panel, for the insights. I don't want to shortchange the poster session, which is starting now. So I believe, correct? I've got the agenda right? Okay. So please, I want to encourage you to make your way down to the other end of the building to engage with the PIs. But before you do that, please, a round of applause for my colleagues here in the front. Thank you.